Hello, hello. Everybody's here? Well, I'm here also, and we're here to go and play with the math counts problems from this year. This is the Math Counts chapter Invitational competition, and we're going to be playing with the problems from the target round. Now, as I've mentioned many times in these kinds of collaborations with math counts, the problems that we're going to do today are copyrighted. These are property of math counts. So please don't reproduce them without permission. And in particular, I want to emphasize this is an official collaboration with math counts. So we actually went and we have their permission. All right, but that's a real pleasure because as I've mentioned in many of these live streams, math counts is how I got really interested in math when I was a middle school student. And so, I mean, it's a real pleasure to be able to give back to the people who are now playing with these problems a few years later. All right, that's enough talking about how old I am. Let's keep going. So we're going to continue with where we left off. And if you remember where we left off with a crazy problem. It was the last problem of the sprint round. It was pretty hard. It combined both number theory and combinatorics. Now, if I want to go on and talk about the next round starts with the target round, and we're going to go back to the beginning of the competition in the sense that this is question 1. So hopefully we can do it. All right, what do we have here? Max is buying hot dogs and buns for dinner. If hot dogs are sold in packages of 6 and buns are sold in packages of 8, what is the least positive number of hot dogs that Max must buy so he can purchase exactly the same number of buns? Okay, so I have 6s and I have 8s, and it looks to me like I need to have something that's just a least common multiple of 6 and 8, because I have 6s and 8s, right? So in that case, what's this? Well, actually, we saw something at the end of the last session, which is 6 is 2 to the first times 3 to the first, and 8 is 2 cubed, and so the LCM is 2 to the power, the bigger of the two powers that we see. So 2 cubed times 3 to the first, and that's 8 times 3, which is 24. And the LCM of two numbers, actually, what I emphasized at the end of the last Math Counts live stream was that you can take the powers of the primes and you take the maximums of the powers of each prime. That's because I need to have something which is a multiple of them, so the number of 2's better be at least 1 and at least 3. Okay, make it be 3. That's what we just did here. Okay, let's see. People say this one was easy. Well, it is question 1. Question 1 is supposed to be as doable as possible, and we can have 24 hot dogs. Next question. Number 2. The square card shown in figure A with area 16 units squared, that 2 is supposed to be up there, is folded twice along the dashed lines to get the square shown in figure B. So there are dashed lines. I can't quite see the squares. Okay, but I'm going to say I'm guessing that this looks like a quarter. We're folding it twice. So I'm guessing that what happened here is I bet that the picture got a little bit hard to see. Let's pretend that's what happened. So you fold and you fold, all right? And after you fold and you fold, then the scissors are used to cut through the folded square, and 1/4 of the folded card. Okay. Oh, yeah, it's removed. Good. So 1/4 of it is removed like this, okay? And when unfolded, what is the area of what remains of the card after the removal? Oh, this is neat. Well, you know what? If you remove 1/4 of the folded card, you're removing 1/4 of the area. It works for the whole thing because you've folded it all together, and the amount you're removing is the same fraction of every one of the quarters. So we're removing 1/4. That means that the amount that remains is 3/4 times whatever was the area there was before. And the area was 16 units squared, so that looks like 12. All right, my answer is 12. Let's see if this is correct. Here we go. It is, so that's the correct answer. Next question. Don't worry, these are going to get so hard by the end that we're going to be wondering how to do these. All right, Cindy has been given 4 chores to complete today. Vacuum, mop, dust, and laundry. It's a good day. Because Cindy finds doing laundry especially unpleasant. Maybe it's not a good day. She wants to do that chore last. Given this, in how many different orders can Cindy complete her chores? Okay, laundry is last. Although laundry is especially unpleasant, it does help to do laundry first so that you can wait for the clothes to wash and then eventually you'll have clothes to wear, as opposed to doing it at the end and being like, oh my gosh, I forgot that you need to put the clothes in the dryer too. Now what am I going to do? Anyway, I had to do that when I was in college. So if I vacuum, mop, dust, and laundry is last, I just need to rearrange the three things, right? So I've got like vacuum, mop, and dust. So those three things will go in some order, and that's three different things to rearrange. 3 times 2 times 1 is the number of ways to rearrange three things. 3 ways to decide which one goes first, 2 ways to decide which one goes second, and 1 way to there's only one left to go last, okay? When I said 2 ways to decide what goes second, that's because you already stuck one of them first. So that's 6. Let's see if this is right. If you can tell, I'm trying to, I saw somebody in the chat. Somebody in the chat said, hey, this is so exciting that this is 3 factorial. We write the exclamation mark to mean 3 times 2 times 1 because we're so excited that we're multiplying lots of numbers together. So 6, okay, let's see. It is. All right, next question, question 4. In the dice game 0, a player rolls 6 standard 6-sided dice and then scores points for certain combinations as shown in the table. A die cannot be used in more than one combination. For example, a player who rolls 1, 5, 6, 4, 4, 6 scores 50 points, while a player who rolls 1, 4, 4, 4, 1, 4 scores 250 points. What is the probability that a player scores 0 points on a roll? Express your answer as a common fraction. Oh no, there's like all these different ways. Oh, okay, well in that case, to score 0 points, it's just like I better lose everything, right? This almost looks like poker or something. But the question is just asking about 0 points. 0 points is very few points. So I'm reading this carefully. When I look on this screen, which is where I'm drawing, it's a little bit easier for me to read. Over there I gotta squint. I guess I'll squint. But I'm seeing this thing, I'm like, okay, how do I avoid all of these, right? If I want to avoid all of these, well, there's a few things which, if I want to avoid them, look, if I avoid 3 of a kind, I also don't have 4 of a kind, and I don't have 5 or 6. So I'm going to say that some of these are redundant. This is redundant, this is redundant, that's redundant. If I didn't get 3 of a kind, no way am I getting any of those. Because I'm trying to say, how many ways can I not get any of these, okay? What else could I try? The number 1, okay, so now I'm trying to say, let's try to avoid this, right? If I'm trying to avoid this, 3 pair. 6, 6, oh yeah, here's something else. Suppose that I don't get the number 1. Then good luck getting 6 distinct, because you're not going to get 1 in the 6 distinct. See, I'm saying like, ignore that one. That doesn't even exist. So now what I have is I need to see how many ways do I not get this. Not get either 3 of a kind or 3 pair or the 1 or the 5. So the only numbers I get to play with are 2s, 3s, 4s, and 6s. Okay? And now the number of ways I can make, something with 2s, 3s, 4s, and 6s, the order I think matters. Is that right? I'm trying to look. I'm going to guess that the order matters because the player rolls 6 standard dice, okay, for certain combinations. And I see that the way the combinations are listed are in order. All right, so in that case, I'm going to think of ordered things. And if I have 4 different possibilities, this is giving me 4 ways to choose the first one, 4 ways to choose the second one, 4 ways to choose the third one, and so on. 4 to the power 6 different total possibilities. But now I have to rule out the ones that are bad, okay? How do I get 3 of a kind? I need to rule out the ones where I have 3 of a kind and I have 3 pair. Which is easier? Well, 3 pair. Let's get rid of the 3 pair. Because I also can see if I got 3 pair, you don't have 3 of a kind. These are 2 different things. So now we're going to take away some of the things. How many have 3 pair? Well, the way to get 3 pair is I've got to decide 3 numbers to use out of these 4 numbers. How many ways can you choose 3 numbers out of the 4 numbers that I have? It's 4 choose 3. But that's actually clear. The number of ways to choose 3 of these to use is the same as the number of ways to choose one not to use. And there's 4 ways to do that, right? So that's going to be 4 times. And of course, if I've decided that I want to have, okay, these 3 particular numbers, 2, 3, and 4, how many ways can I rearrange those? Well, that's a question of permutations. If I want to know how many ways can I rearrange this 2, 2, 3, 3, 4, 4, the number of ways to rearrange that is there's 6 factorial ways to rearrange 6 things, because I have 2, I have 6 symbols. But now, on every one of those rearrangements, the ones where I have a 2 here and the second 2 there is the same as the first 2 here and the second 2 there. So I have to divide by the number of ways that I could change the ordering of the 2's. If you imagine like the 6 factorials, if I'm distributing 6 things which are all distinct, and here they're not quite all distinct because I can tell that these 2's are actually the same. So I have to divide by the number of ways to rearrange the 2's, rearrange the 3's, and rearrange the 4's if it so happened that I was dealing with 2, 3, and 4. Okay? So this is the number of ways that I could get 3 pair. The number of ways I can get 3 pair is 4 ways to decide which 3 numbers times that thing, and that's going to tell me how many ways that I could like rearrange those after I decided the 3 symbols I'm using. That is 6 times 5 times 4 times, that was supposed to be a 4, 6 times 5 times 4 times 3 times 2 times 1, the 1 doesn't matter, divided by 2 times 2 times 2, and I'll cancel those. So 2 and 2 gives you a 4. This 2 hits with that 2. I have a 6 and a 5 and a 3. 6 times 5 is 30. And I have 30 times 3. Okay, so 30, yeah, that was 30. 30 times 3 is 90. 90 times 4 is 360. Okay? We're going to have to subtract from 4 to the power 6. By the way, as you know, I'm very lazy. I can't bring myself to bring out my calculator. So I know that 4 to the 6 is 2 to the power 12. I know that 2 to the power 10 is 1024. So this is 4096. Okay? Good. I know my powers of 2 because I do a lot of computer programming. All right, the last one is how many ways can I get 3 of a kind? Well, if I want to get 3 of a kind, oh my gosh, this is a really tricky problem because I could have like 3 of a kind and 3 of the other kind. Or I can have, wait a second. Now I'm thinking, what's the easiest way that I can knock these out? So if I want to get 3 of a kind, oh, neat. So I have these 4 numbers I can play with. And it's going to be that there's one number which has at least 3 up here. And then I do some other stuff, anything I want with the rest of them. Is that what I want? Oh my gosh, this is actually really tricky. Let's go. These are actually all related to each other. So I'm trying to think. How can I think about this to get 3 of a kind? Aha. So I have these, because I'm thinking about rearrangements too, which is tricky. This is a really hard problem now. Let me see. So if I have to do, when I say really hard problem, it's like, remember we had only 6 minutes to think about this. So if it's 3 of a kind, I'm trying to say like, do I want to have, I'm thinking of how to handle all of the rearrangements that we might have in here. So for example, if I was going to put, my 3 of a kind meant 3 of them being 2, then I can do like, 3 of the 2's and then 1 of each of the other ones. That's one way. Or I can have, because I need to think about how many repeats I have. Okay, let's play with this, all right? So let's now think of the other kind, which is like 3 plus of a kind. Maybe this is not the most efficient solution. Okay? I'm going to call the numbers A's, B's, and C's because that's the different kinds of things it might look like. They might be like A, B, C, D. That's one way to get 3 of a kind. Another way to get 3 of a kind is A, and then maybe B, B, C. And another one is A, B, B, B. These are the different kinds of patterns that I could have because I could have like 3 of one kind and 3 of another kind, right? And that's 3 of a kind. Or I could have 3 of a kind and then 2 of this and then 1 of that. Or I can have 3 of a kind and then 1 of each of the rest. But there's even more. I could also have 4 of the A's. If I have 4 of the A's, then I will have to, if I have 4 of the A's, trying to think how I want to do this. If I have 4 of the A's, I could have like a B and a C, meaning those two are different. Or I can have 4 of the A's and a B, meaning those two are the same. Or I can have 5 A's and a B, or I can have all 6 A's. This is too many cases. Wait a second. No more than 3 of each. So I'm going to look in a different way. This is too hard. When I say this is too hard, what I mean is this looks like it's going to give me too many cases. It looks to me like it actually would have been easier to think about this problem to say, wait a second, I have these 4 numbers, and I'm allowed to take either 0, 1, or 2 of each of them. Maybe that's the better way to do this. Yeah, this subtraction thing isn't working. You're watching, like, I'm looking at this and I'm like, wow, that looks like it's pretty hard to do it this way. So let's think of it differently. I'm like, let's not try to do this where I'm subtracting out all of these. I have too many cases. This is horrible. Bad. Scary. So instead of subtracting, you see I'm flipping around now and I'm saying, no, I think I want to think about it differently. I want to say, how many ways can I make 6 of these numbers where I never get 3 of anyone, so I have at most 2 of each, and I don't have 3 pairs? Maybe that's the way. So if I want to say, I'm allowed to, oh yeah, this is so much better. If I want to say, no, it's less than 2 of each. That's what I really want. Then what might this end up looking like? Then it has to be like, well, maybe I've got 2 of the A's, and 2 of the B's, and a C and a D. I'm saying like these might be the 4 different kinds of numbers I have. I mean, they are from 2, 3, 4, and, 2, 3, what is it? 2, 3, 4, and 6. I've got 4 different symbols. That's one way. And A, B, C, and D are representing different things. And when I look at this, I say, hang on, is that the only way? Yeah, that's the only way. I need to use 2 of one, 2 of another, and 1 of one, and 1 of the other. I think that's right. That's the only way to go and make 6 things if I'm allowed to use at most 2 of each. And I can't have like 3 of them all being pairs. Oh, neat. So now I just need to know how many ways can I make things that look like this, where I decided that there's going to be 2 of one number, 2 of another number, 1 of this number, and 1 of that number. Okay, now I need to think about ways that I can do rearrangements. And I want to make sure I don't overcount in the wrong way. So let's see. I have to decide what are going to be this A, B, C, and D, but there's also a danger that some of these things get repeated counting. So I can decide that. As you can see, I'm thinking about this because the scary thing here is if you overcount we've already found out this is the way you want to go. This is the simple thing we want to do. And now we want to make sure we don't actually count things like too many times. If I just went and tried to do all the rearrangements of this thing, okay, then as you can see, I'm thinking. I'm like, all right. So I think here's how I'm going to say it. Because there's 2 of the numbers that are out of the 2, 3, 4, and out of the 2, 3, 4, and 5. 2 of them get doubled and 2 of them get singled. Let's do it that way. All right. So when I look at this, my numbers are 2, 3, 4, and 6. 4 and 6. All right. I've got 2, 3, 4, and 6. And what ends up happening here is that half of these numbers end up in doubles, and half of these numbers end up in singles. So how to choose which 2 of them are doubled? Well, there's 4 numbers here, right? There's 4 numbers, 2, 3, 4, and 6. How many ways can I do that? Well, 4, choose 2, which is 4 ways to choose the first one, 3 ways to choose the second one, divided by 2 ways, because it's like if I chose the 4 as the first one and the 3 as the second one, that's the same thing as if I chose 3 as the first one and 4 as the second one. So that's equal to 2 times 3, which is 6. So now that's the number of ways I can decide. Once I've made that decision, now I have something that looks, for example, like, this is how I think of it. This looks, for example, like, oh, it's going to be something where there's like 2, 2, 3, 3, 4, and 6. That's what I'm playing with. So after this line, I know what are the numbers I'm playing with. And every different outcome of this line gives me a different bunch of 6 numbers. That's how I'm going to think of this, okay? You forgot what was the problem. The problem was very complicated. It was this thing. How many ways can you get, what is the probability actually that you get 0 points on a roll? Okay, and the number of ways to get 0 points on a roll means you avoid all of this stuff. None of this stuff happens. And we boiled it down to, it has to look like this, A, B, B, C, and D. And now, in that case, what I've gotten here is like, all right, now I need to know how many ways could I rearrange this? If I know it's going to be this, well, now I actually have and what I wanted to emphasize is everything that pops out of this line is giving me a different collection of 6 things if I don't even care about the ordering. All right, that's the number of ways to choose 2 of them, half of them to be doubled. So now I want to know how many ways could I rearrange this. The number of ways to rearrange each one is, well, there are 6 things altogether that you could rearrange, except that there's 2 ways to rearrange the 2's, and there's 2 ways to rearrange the 3's. These are both 2 factorials, actually. So what's actually going on here is I'm doing this classic type of problem, which is I've got something, how many rearrangements are there? It's going to be the factorial of how many things there are to play with, divided by the fact that, well, these could be twiddled and those could be twiddled. So the number of ways to rearrange is 6 times 5 times 4 times 3 times 2, times 1 doesn't make a difference, over 2 times 2. Cancel out, the 2 times 2 is 4. Now if I want to multiply all this, actually, I see that I'm going to be doing some probability at the end, so let's not multiply everything. All I know, I mean, not work out a number. All I know now is that here's how to choose which 2 of them are doubled. And here, for each one of those, I get to do a rearrangement. I want to multiply all this, and the answer is a probability. The answer is divided by 6 to the power 6. Because that's the number of ways to get 6 outcomes when you roll dice. On top, I have a 6 times another 6 times 5 times 3 times 2. Okay, that's what I've got. Let's cancel. This 6 cancels that 6. This 6 cancels that 6. This 3 times 2 cancels one of those 6's. And the answer that I end up getting is 5 divided by 6 cubed, which is 216. Okay, we spent a long time trying to work this thing out, and somebody actually did work out, like, what is 6 to the power 6? I don't use a calculator, so I don't know. This may or may not be right, but let's go and find out. Let's see. It is! It's right! Okay, so what you just saw is that we would have absolutely run out of time on that problem, okay? We would have run out of time, and these problems are getting hard. This is getting scary. But now let's recap what exactly happened. What you saw is I said, oh yeah, let's rule out a bunch of stuff. And now, okay, let's go and count how many of these. I know I can do that. That's not that hard. And I was like, I know how to do that too. 3 pair, I know how to do that. That's not that hard. Then I started to be like, how do I find out there's no 3 of a kind? And I got extremely scared because there's like all these different patterns that could come. And I was like, math counts, you won't do that to us. So in that case, it was like, okay, let's work on the other direction. This is hard because there's too many ways to let there be many of a kind, right? Many of a particular kind. So it becomes the pattern we want to see is where A, B, and C, and D are different things. And it just so happens that there's 2 of one, 2 of another, 1 of one, and 1 of the other. And then what I was thinking about is, how do I make sure I don't make a mistake of like counting the same thing twice? And if you can see, the key point where I got confidence is I said, look at that. Every different outcome of this purple line is going to give me a fundamentally different collection of 6 numbers, with repeats, of course. And that's how I know, after this line, I can just go and say, stare at these 6 numbers, how many ways can I rearrange? All right. Doesn't this end at 7:30? It sure does. All right, question 5. Oh boy. A US quarter is 0.069 inches thick. Clayton Kershaw earned $33 million for the 2017 Major League Baseball season. If Kershaw received his entire 2017 salary in the form of a single stack of quarters, what would be the height of the stack in miles? There are 5,280 feet in a mile. Express your answer as a decimal to the nearest hundredth. Now, this is the reason why you don't want to be paid in quarters. All right, so the whole thing is $33 million. So I want 33 million. That's 33 times 10 to the power 6. All right, that's the number of dollars. But, oh, these are quarters, so times 4. All right, and then I need to go and multiply by the thickness, which is 0.069. That's the number of inches so far. That's a lot of inches. Okay, the next thing I do is I have to take the inches and convert them into miles. So if I want to convert inches into miles, first you divide by 12 to go from inches to feet, and then from feet to miles, 5,280. And now we need to actually go and work this thing out. We need this as a decimal to the nearest hundredth. All right. Out comes my calculator. My calculator is this thing. No smartphones allowed on the contest, but I promise you I'm not calling a friend. I'm actually trying to struggle with the calculator on this phone, which is actually less convenient than the calculator that you guys use. All right, 33 times 10 to the power 6. 10 to the power 6 is 6 zeros, okay, and then times 4, and then times 0.069 inches thick, all right, divided by, now this is the tricky part, you want to divide by both 12 and 5280. Divide by 12 and 5280, and when I'm done with that, I got 143.75. Wow. 143.75. Okay, so I think that's the answer. Hopefully I didn't make a mistake. I find it kind of nifty that my calculator somehow told me that this was 143.75 without any more digits. A bit of me is like, wow, really? Maybe MathCounts gave us some numbers for which it actually comes out this way. Anyway, let's go and see if this works. Yes, it does. And now let's go and buckle up for question number 6. These are getting hard. In rectangle ABCD, the length of side AB is less than the length of side BC. When diagonal, let's draw a rectangle first. So AB is less, all right? So I'm going to draw this thing. AB is less than BC. So that tells me it looks something like this. AB is less than BC. Next, when diagonal AC is drawn, hello, and a line segment from vertex B to diagonal AC is drawn so that the segment meets AC at a right angle. Okay, this kind of thing. Right angle. All right. Rectangle ABCD is divided into 3 regions. They sure are. Whose areas form an arithmetic progression. The ratio AB to BC expressed as a common fraction in simplest radical form is so whatever. Okay, I like these kinds of questions. All right. So oh, this is so neat. All right, so when I look at this thing, there are actually a lot of similar triangles in this picture. So we're going to do this one faster than we did that combinatorics one. Watch, we got some neat angles which are equal to each other. I'll write a single tick on that one, since it looks a bit smaller. Double tick on that one. Well, did you know that the single one plus the double one adds up to 90 because of that? Well, here's a 90. And so here's another right triangle. So if I've got this right triangle, I already know that single plus double tick is 90. So here's a double tick. That means that over here is a single tick. Oh, well, I mean, 90 is also on that side. If there's a single tick here, the sum of the angles of a triangle is 180. So this guy needs to be a double tick. That's kind of interesting. Oh, did you know that the single tick here plus a double tick gives you 90 because that's a rectangle? And since I've got a right angle here, this double tick and that single tick plus the right angle make 180. That means this is a single tick. So what have I got? I've gotten like 3 similar triangles. That's kind of neat. And so since these are 3 similar triangles, I know something about the ratio of their areas. Okay, so the areas will form an arithmetic progression, but they're all similar. Similar means like they have all the same set of angles, right? I've got single tick, double tick, right angle. Single tick, double tick, right angle. Single tick, double tick, right angle. All similar. In that case, if only I knew something about the lengths. So let's look at the lengths, okay? Why am I doing this? I'm going to label the lengths. So I want to actually label the hypotenuses. Let's call this A. Let's call this B. And let's call this C. Okay, these are actually 3 hypotenuses. The hypotenuse of the little guy has hypotenuse A. Hypotenuse of this guy has B, and the hypotenuse of this guy has C, right? Now, if I know these 3 hypotenuses, or hypotenusi, or however you pluralize that, does anyone know what the ratio of areas is between a triangle with hypotenuse A and a triangle with hypotenuse B? Ratio of areas, wait a second. Arithmetic progression. No. Let's not do that. Let's not do ratio. I actually do want to think about ratio of areas, but what I want to think more about is if I'm doing something with ratios, actually it is safe. It is safe. The point is, if I have something whose hypotenuse is A, then the area of this triangle is actually going to be like a squared times some number. And the area of this triangle is going to be b squared times the same number. That's the important detail. Okay, that's actually what I'm using here. I'm using the fact that if I went from some triangle to a similar triangle, okay, whatever the area was, if this area was something and I want to go to that area, the way that this works is, oh, here's actually a nice visual way to see it. Let's do it that way. Nice visual way to see it. Look, I drew a square. These are supposed to be squares. They don't look like squares at all. But this is a square, and here's another square. Sort of a square. Yeah, a square. So I drew these squares. Do you see how the fraction of the square that's in here is the same as the fraction of that square that's in that triangle? And the area of the whole square is a squared. The area of this whole square is b squared. The area of this whole square is b squared. And so actually the area of this thing is going to be of the form, let's make up some number. What's a random number I haven't used yet? X. It'll be x a squared is the area of this piece, where x is the fraction of the area of the square that is the triangle. The area of this triangle is going to be xb squared with the same x. I'm just using x. I don't care about x. I don't want to solve for x. I don't want to solve for x at all. But I'm going to say that whatever the x is, the area of this triangle is going to be x times b squared. Because the fraction of the whole square made, that is this triangle, is x fraction. And then this particular area will be x times c squared. Now, why did I do that? I did that because now I know that xa squared, xb squared, xc squared are in an arithmetic progression. Xa squared, xb squared, xc squared are arithmetic progression. Okay, that's nice. But now, as I look at this, I'm like, okay, well, in that case, I know that a squared, b squared, and c squared are in an arithmetic progression because they just happen to go, if I have an arithmetic progression, divide everything through by x, and I still have an arithmetic progression. A squared, b squared, c squared also. All right. Now, I know that a squared, b squared, c squared satisfy an arithmetic progression, and I also know something else about a, b, and c. What else do you know about a, b, and c? There's actually a nice fact about a, b, and c. I've got a Pythagorean theorem here. See? That's an a, that's a b, and that's a c. So I also know that a squared plus b squared equals c squared. All right, let's collect these facts on the next screen. I know from the Pythagorean theorem, a squared plus b squared equals c squared. Now, how would I express that a squared, b squared, and c squared are in arithmetic progression? Well, look at this. This is actually something I learned when I was a PhD student, but this trick is neat. If I know that there's an a squared here, there's a b squared here, and there's a c squared here, and they're equally spaced, arithmetic progression tells me that b squared is the average of those two, right? B squared has to be the average of the a squared and c squared. So this is a squared plus c squared over 2, which gives me a nice equation. 2b squared equals a squared plus c squared. So that's another equation I have. 2b squared equals a squared plus c squared. Now, the question is not asking me to find all of a, b, and c. The question is asking me for a ratio. Oh no, these are called a and b. But, oh my gosh. I'm supposed to write it like this and multiply the thing under the radical by the thing on the bottom. All right? Even though I used a and b in my thing, those are different a and b. But now I want to know ab to bc. I want to know this a divided by b. That's what I'm curious about. I'm curious about a divided by b. A divided by b equals question mark. So now if I have this bunch of equations, I don't like c at all. So what can I do? I can subtract the equations. I can go and take the second equation and subtract the first equation. Watch what happens. I'm happy to do this because what I see is that the c squares are going to cancel, and all that's left is a's and b's. So all I'll be left with is negative a squared plus b squared is equal to a squared. Now this is good because I care about a divided by b. So let's go and add a squared to both sides. B squared is equal to twice a squared. Now I can make a squared divided by b squared. Just divide by b squared. Actually, also divide by 2 at the same time. So I get 1/2 is equal to a squared over b squared. Are people happy with what I've just done here? I've just been like, all right, I have these two equations. Great. I need to go and figure out what is a over b. And the way I'll figure out a over b is I'll get rid of the c. C is annoying. Once I get rid of the c, I have only an equation with a and b, which I'm trying to isolate into an a over b type of form, which I can see, because that tells me that 1/2 is equal to a divided by b whole thing squared. Well then, does anyone know what's a over b? Then a over b is going to be 1 over the square root of 2. And it won't be negative because these are lengths. But I can't write 1 over root 2. I need to rationalize the denominator. The way you rationalize the denominator is you multiply it by 1, which is the same thing over something else. And so I get that this is root 2 over 2. Now the question was asking me to go and multiply together these two numbers. All right? So since I was supposed to multiply together these two numbers, then the answer is going to be 4. Now I do want to check to see if this makes sense. All right? So I would say that the answer is now 4. I'm supposed to multiply those two numbers together. And does the question make sense? Do the numbers make sense? Yeah, I guess so. If this to this is 1 is to root 2, oh my gosh. Yeah, this is totally true. This is a piece of A4 paper. This is A4 paper. If you are in Europe, or if you have access to some piece of A4 paper, you can actually legitimately do this. And I can sort of see in my head that this would work. Where what you do is A4 paper has this ratio, 1 is to square root of 2. And then you would be able to fold it diagonally, and you'd be able to fold it again diagonally. It should work. Let's see. Is that the answer? It is the answer. Okay. Yes, so if you go to Europe, grab an A4 paper, the whole thing will work. We have 24 minutes left to go and try to do the last two questions. And just in case you were curious, the target round is supposed to be 4 sets of questions. Each question set, you have 6 minutes. 4 times 6 is 24. We will now use the entire time that's usually used for the entire round to try to do the last two questions. Because it looks like these are getting hard. Oh, can I show the question again? Yes, I can. The question is here, okay? It's just saying like, got a rectangle of A4 paper. Fold it in the diagonal. Fold it another one, which makes this like right angle thing, and then you're good. Oh, really? Somebody here is from Europe and once had this in an exam. Cool. Okay. I should tell you the reason why I was very optimistic that this would work, why I went on this road, is because I said, I see that these hypotenuses are going to tell me something about the areas. It will be with the squares of the hypotenuses. And then I was like, oh wait, the squares of the hypotenuses also are related to Pythagorean theorem. Therefore, I can probably put something together. That's how I knew. Beware number 8. Oh no, oh no. Okay, somebody's warning us that we better go. All right, if C is the temperature in degrees Celsius, the temperature in degrees Fahrenheit is given by this formula, 9/5 C plus 32. Just in case anyone's watching, this, of course you guys are watching, or else you wouldn't be watching. Anyway, 9/5 C plus 32. It's kind of the funny thing to say, like, is anyone asleep? No one should say yes. But anyway, so we got this thing on a cold winter day. Temperatures in degrees Fahrenheit is the additive inverse of the temperature in degrees Celsius. What is the temperature in degrees Celsius? Okay, so what we're saying is that the Fahrenheit, which is this thing, just happens to be the additive inverse of the temperature in Celsius. So I think all I'm saying is like 9/5 C plus 32. Whoops, that happens to be minus C. That's all this question is saying. So 9/5 C plus 32, that's what you'd read in the Fahrenheit, except that that's minus the Celsius. Okay? And so I need to go and figure out what is the C. So let's put it together. Let's move this one over here. So adding 1 to both sides, that gives me 14 over 5. C is equal to negative 32. So C is equal to, what is this? Yeah, I got to do some division stuff. So it's negative 32 times 5 over 14, cancel time. So the 14 and the 32 divide by 2, so I get 7 here. Divide by 2, I get 16 there. All right. So I get this thing, which is negative 80 over 7. As you know, I'm lazy. I'm not going to pick up my calculator. So minus 80 over 7, let's make it a mixed number. It's negative 7 times 11 is 77, and then there's 3 over 7, okay? And if I want to convert this into a decimal, actually I happen to know that 1/7 is 0.142857 ... It's a repeating thing. And 3/7, if you imagine multiplying that by 3, you'd get something that starts with 0.42, because 14 times 3 is 42, and it's actually the same sequence of the same 6 numbers, 28571. That's a really neat fact. I don't have time to prove it today. But so that's going to give me minus 11.4. I'm asking myself, does this make sense? Is this a cold winter day? Yeah, this makes sense. A cold winter day could be negative 11.4 degrees Celsius. If it was like negative 5,000, I'd say no, no, no. And if it was like over 9,000, I'd be like no, no, no. But negative 11.4, I think I'm okay with this. Yes. And now, the grand finale. How many ways are there to color the 4x4 grid shown so that each unit square is red, blue, green, or yellow, and so that each unit square is the same color as exactly 2 of the unit squares that share a side with it? Whoa, okay. So I get 4 colors to use, and each unit square is the same color as exactly 2 of the unit squares that share a side with it. Well, how do I do that? If I want exactly 2, can't be 1. So I'm gonna start playing. Okay, color time, color time. I'm gonna look in the middle things. Oh wait, no, start from the side, start from the edge. Hi, you are pink now, and so if that's supposed to be the same color as exactly 2 of the unit squares that share a side with it, I don't have much choice, right? This is the same color as 2 of the unit squares that there's only 2. So if there's only 2, okay, better look like this too. Okay, so I might change my mind on whether it's really going to be pinkish purple. We'll change that out later. But I'm like, that needs to be the same color as those 2. All right. Similarly, something happens over here. Something happens over here, and something happens over here. I've just found out that the corners are all these L shapes, which are all the same color. The next thing I look at is I go and say, what else could I say, right? You know, for example, so I got some cases. So one case is like, well, what if I continued? You know, I know that the corner things have to be all the same color, right? So if I continued this way, now my rule about each of these is the same color as exactly 2. What I now know is that this guy is not like it's not this pinkish purple color, because this thing is already the same color as exactly 2, so that better not be one of them. And if that were the case, then this would also be a not. How would I pull that off? The only way to pull that off, by the way, is then this thing would need to be exactly the same color as 2 things next to it, right? And there's only 2 more next to it that are potentially not that. So what I'm saying is, if these are the same, I'm going to start like writing down what I'm doing. If they are equal, I don't have the space to write same. Oh, I know how to write it. Same. Okay, so if these 2 are the same color, what I've just found out is that this is some other color, legitimately other color, but furthermore, these 2 have to be the same, and that one has to be the same too. These 3 all have to be the same as each other. Okay, and just to emphasize that they're different, and it's not, it's like, well, this and this, yeah, exactly. These are all the same, right? The way I got that, remember, is I was like, because this guy's already satisfied, it's the same as those 2 which are next to it, well then this better not be, because it's supposed to be the same color as exactly 2 of the squares next to it, and there can't be 3. So now I know that these 2 are not the same color as those, but then when I looked at this one, I was like, wait, how could this one be the same color as 2 around it? It's not the same color as those, so I have to use both of these. Oh, but wait, I can make that argument symmetrical. See this guy? This guy needs to be the same color as 2. And it's not that. So that means that all of these 4 are the same as each other. So the simple thing of like, if those 2 were the same, if the top thing and the bottom thing, if they're the same, then all of this is like different and same as itself in a different way. Well, in that case, what else could I have? Now I'm kind of stuck. Look up here. This guy needs to be the same pinkish purple as two other people around it. Oh, well, that's one, so this one better be the other one. So now I'm forced to make that one also pinkish purple, and I already know that the L shape is all the same color. The same logic is going to tell me this lonely person needs to be the same color as two. Okay, now I've got to fill it like this. So what I've just found out is, if these two are the same, it looks like this, where there's one color outside and one color inside. How can I decide? Well, I've got 4 colors to play with, and so the number of ways to do that if they are the same, which is if the borders are well, if there's 2 equal, okay? If there's like the same between 5 equals 9. If 5 equals 9, that's how we thought about it. Okay. I feel really funny on a math live stream saying if 5 equals 9, but I hope you understand what I mean. It's like the box 5 and the box 9, all right? Like 5 is obviously not equal to 9. Or else I could prove that like 4 equals to 0 or something. But if 5 equals to 9, then what I found out is like there's 4 ways to decide what is the color going on the outside. Oh no, now everyone is going and like proving crazy math. Then there's 4 ways to decide which is the color that goes on the outside. Once that one's been decided, I need a different color. So there's 3 ways to decide which color goes on the inside. And there's 12 ways. So I've just dealt with the situation if 5 equals 9. But I have another possibility. 5 is not equal to 9. Well, I guess that's news. So if 5 is not equal to 9, let's redo it. I don't have many pictures that I can use, but I'll just draw it. I erased it, I'll draw it here. Next. Now 5 is not equal to 9. Oh no, but these are all the same as each other. All right. Oh boy, but if that's the case, how is this supposed to be the same color as exactly 2 squares that share a border? Well, not that one. So it's the same as that one, and that one better be the same too. So now I know that that's forced. I have no choice. This square, in order for 5 to be happy, both of these have to be the same color as 5. In order for 9 to be happy, both of these, both of the squares around 9 have to be the same color as well, because 9 is already different from 5. Now if I keep going, look at this. 2 is already happy. It's got 2 colors that are same as it. So I need something here which is different. Now here's one tricky thing. Different, it could actually be this this color. It could actually be this blue. But I'm just going to emphasize it's something, okay? It's something. It's not necessarily different from blue. And if you can see what's going on, that's forced. I'm always forced to do that. Once I start here, the L shape's got to be the same. And in order to make, let's say, this square number 3 happy, I have no choice. It has to make 2 of them be the same color as itself. So I'm forced to be here. Okay, and now once I do that, I know that over here, I need to choose a different color. I need to choose a color that's not whatever I used up there and not whatever I used over there. By the way, it could actually be this pinkish purple. But I'm just going to use this first. And if you can see, I'll finish it that way. So the other possibility is, if 5 is not equal to 9, then what I need to have is that somehow these 4 pieces need to be such that there's not 2 of the same color right next to each other. Okay, so I can't put 2 of the same color next to each other. 5 not equal to 9, then somehow like 4 corners, well, I'm not going to draw an arrow to the right, there's a lot more dot dot dot. The 4 corners each are the same color, but no nearby corners are same color. When I'm saying corner, I'm talking about that entire thing. That's a corner. All right, how could I do this? Well, one way to do this, actually this is the deep thing. There are ways to do this with fancy combinatorics, but since this is a middle school math competition, I'm going to do it in a way where you can do case counting. All right, so I have these 4 corners, and I'll abstractly draw it like this. I'm actually a network theorist, so the way I often draw them is I'm like, well, I've got 4 corners, and I'm going to abstractly represent it like this. This is actually, technically speaking, this is called a graph. Okay, I can't help but say that. This is called a graph, okay? And this is an area of math called graph theory. Now, what I want to do is I have 4 colors. I'm really lazy. The 4 colors are called 1, 2, 3, and 4. And, well, I think I should just write like A, B, C, and D as the colors, just to indicate what I could have. I could have that I have an A, I could have a B, I could have a C, and I could have a D. That's one possibility. All four are different. And here by A, B, C, and D, I'm emphasizing that they're all different. There is actually a systematic way to do this, but that would be out of the scope of today's live stream. But so if I have A, B, C, and D, that's one way. But another way I could do it is I could do like A, B, A, and C. Does that make sense? I could do that also. And don't forget, I can do like rotations of these things. So trying to think if I want to just go and use the more sophisticated approach. No, I don't. So I have this thing, right? So these are the possibilities. And then there's another possibility, which is like if I go A and A and B and B. These are three general categories. Do you agree that every way of coloring where you have four colors to play with, and I'm not allowed to use the same color on things that are next to each other, it'll have to be like this, this, or this. And you might say the second one has a slightly different variant also. The second one also has a variant where I could go, got this, 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 and I could go where these are the A's. And then this is the B, and this is the C. Does it make sense that everything has to be one of these? Either they're all four different, or there's like a pair that's equal, and it's just a diagonal, or it could be the other diagonal, or it could be both diagonals are equal. These are the only possibilities. And there is a fancy way to do this, but that's actually a serious combinatorics class. Now, if I want to do this, okay, how can I decide what goes here? Well, the number of ways I can fill that guy in is I can say, I've got four colors to play with. Who wants to be A? I'm just like calling for players, right? Who wants to be A? Okay, so there's 4 ways to decide who gets to be A, 3 ways to decide who gets to be B, 2 ways to decide who gets to be C, 1 way to decide who gets to be D. That's 24. 24 ways to do this. If I want to know, I like it, you guys are saying me. But then over here, what else could I do? Well, over here I can say, let's stare at this guy first, okay? This particular one. And this is how I make sure I don't make mistakes. That one. So that one is like, who wants to be A? 4 choices. Raise your hand. Who wants to be B? 3 choices of who's left. Who wants to be C? 2 choices of who's left. Now, the only thing I want to check is, did I double count anything? And you didn't. Because you see, if I did this way, and I was like, A happens to be blue and blue. Okay, got blues here. Who wants to be B? Pink. Who wants to be C? Yellow. Great. That's a legitimate drawing. What if this one decided to be yellow and that decided to be pink? Then they're different. So that's going to give me 24. But I know that this one is the same, which is 24, because there are, now they're in this position. So now these two are the same. Okay, so these are all the different possible categories of how I might try to color this thing. And the last one is like diagonals and diagonals, right? So the last one is just going to say, who wants to be A? 4 people raise their hand. Like four people are willing to try different colors. 3 different colors can be B. That's going to give you 12. So now I've just found out the number of ways to go and color this thing. Okay. Well, in that case, let's go and add this up. 24, 24, 24, that's 72. 72, 12, that's, I think it's 84. I want to see what I'm adding. Ooh, look at that, there's another 12. So if there's another 12 there, it looks like it's just going to be 24, and there's 4 of them, right? So what I have here is that, so I have the 24, a 24, a 24 from these, okay? And then I've got a 12, but the 12 is going to add with this last one that I have to do here. But I'm still going to write down what I had is I got to 24 times 3 plus a 12. And so the sum total of everything is equal to, it's actually 24 times 4. There's 4 24s because the last 12 joins with the other 12. 24 times 4, I'd get 96. Could be wrong. Let's go ahead and find out. I actually could be wrong on this. And it could totally be wrong because these are really, really tricky questions. Let's go and find out whether it's right, and then we'll decide whether to celebrate or whether to go and figure out what to fix. Bam! It's right. Okay, yes, so it is 96. All right, and as you can see, we spent like way over the time limit. I have no idea how you guys managed to solve these problems so fast in a math competition. But I guess I should say, if I was in a math competition, I would probably be trying to like scribble stuff as fast as I can. I'm super impressed by any of you who actually did this in the time limit. This is like really, really, really some serious talent. But if you can see what I was trying to do, I was trying to make it so that I don't make any mistakes. And the way I didn't want to make a mistake is I wanted to say, okay, over here, you know, like let's be very cautious. Are they equal or are they not equal? Split into very clear cases. And then suddenly the game became, that one was easy. I could do that. It was just outside and inside. And then that one, the second one, somebody asked, what's the sophisticated way? This is a famous problem. This is a problem called, I have a cycle of 4 things. How many ways can you color the 4 things where you don't make this connection the same color, like both ends on the same color? So if you want to know what's the fancy way to do this, so here's the fancy way to do this. Since you asked, okay, there is a fancy way to do this. So this is called the number of ways to color using less than or equal to 4 colors the vertices. That's actually what those are called. The vertices of this thing. Okay? Now, the way that you can break this apart is you can say, oh, you know, that's easy. That's equal to the number of ways for this thing. No, that's wrong. It's absolutely not. Because, like, there are ways to color. Well, oh, yeah, I should emphasize. What does this drawing mean? This drawing means that if there's a connection, I'm not allowed to use the same color on both parts of the on both of the vertices. Why is it not the same if I open the top? It's because, well, you could accidentally, when coloring this guy where you open the top, you could accidentally have made both of the top the same color. That'd be bad. If you made both of them the same color, that's a legit way for here, but it is totally not a legit here for there. It's totally not a legit way for there. Does that make sense? I'm being like, look at the number of ways I could color the 4 corners of this thing and just use those colors over there blindly, just hoping that the 2 top things aren't the same. No, that's wrong. So what you do is you got to fix it, subtract the number of ways for this where the top are the same. Well, that's kind of weird. What does it mean to color both things on the top the same? Well, that's actually equal to the number of ways for the first one. I'm just writing this U-shaped thing again. Okay? Minus the number of ways for, now here's the leap of insight. How did that happen? Well, the way this happened is I said, look, if I'm going to force those two to be the same, just like make one of them, okay? But connect that one to both of the places that those same things were connected. The reason why that these two are the same number of colorings is because the only rule that this line makes is it says I'm not allowed to use the same color for both of these. So if I go and say these same things, let's like move them really close to each other so you can't even tell them apart. Well, then it looks like this, okay? Because the number of ways to color this, if I color this and I just go and take that top color and I duplicate it, it's going to be a coloring of this U-shaped thing where I never use the same color on both ends of one of these edges, but I actually have the same on top. But look, now we're going to be done. How many ways can you color this thing with 4 colors? Well, just color that guy. If I want to do this one, I'm just going to draw a big thing. How many ways can you color this with 4 colors? 4 ways to decide. Whoa. 4 ways to decide which color goes there. Times 3 ways to decide a color that's different from anything I used. So I used 1, so I choose something different. How many ways can I color this one? Well, I just avoid whatever I used there. There are 4 colors to start with. Avoid 1 color tells me I have 3 choices. It's not 4 times 3 times 2. It's 4 times 3 times 3 because what I do to color this is just avoid that one. How about that one? Choose a color that just avoids that one. Bam! That's nice. 4 times 3 times 3 times 3. How about this? How many ways can you color this with 4 colors so that I don't use the same color on any 2 things that touch? Well, all 2 things touch. So that just means that I can't use the same color ever. Now, how many ways can I use 4 colors for this? 4 ways to decide who goes there. 3 ways to avoid that one. And now I need to avoid both of those, and both of those are different. So 2 ways to avoid those different ones. Let's subtract 4 times 3 times 3 times 3 minus 4 times 3 times 2. That's it. So if I want to factor, this is 4 times 3 times 3 times 3 minus 2. Whoa, that's a weird 2. Minus 2. Do you see what I did there? Because that's 4 times 3 times 2 is the second piece. 4 times 3 times 3 times 3 is the first piece. This is a lot easier to multiply. 3 times 3 is 9 minus 2 is 7. So what I just got is 12 times 7, which is 84. That's what we had. So this is the super slick way to do this thing. I'm sorry if this is more sophisticated than what you were expecting, but I wanted to give you a little bit of an insight that, like, wow, you can actually go and find this without doing like crazy casework. This is actually extremely systematic. This is called graph coloring. And so, yeah, it's a subject that I normally teach. Now, what about the other? Where are the other 12? The other 12, remember, came from the other kind. We either had that 5 was equal to 9. That gave me 12. That was the outside is one color, the inside is another. And the 5 not equal to 9, we were able to get this 72. No, 70, whatever it was. 84. We were able to get 84. And 84 plus 12 gave you 96. All right. So that actually finishes out what we did today. I sincerely hope that you guys had some fun. I am personally very surprised that we managed to get those questions right. These are insanely difficult. I have to apologize. Unfortunately, I have to run off. I have something else that's scheduled at this time. But if you enjoyed these, and if you have random questions about math, I will actually be doing another live stream next weekend on Saturday evening. It's the Ask Math Anything. And you're welcome to ask all kinds of questions there. But for today, I'm just going to say thank you to everyone for coming. Thank you to MathCounts for making these really, really incredible questions, making me struggle. And I hope that everyone here had some fun. I'll see you next time. Bye-bye.